let's create a new file called exploit1.pl. And let's start with a shebang /user/bin/perl. Let's also write this line. This line forces a flush after every write or print. So the output appears as soon as it is generated rather than being buffered. Right, now let's create a new variable called junk and let's give it 256As, which is the offset to RBP register. So after filling in 256As, we will be overwrite RBP register using our exploit. So this is offset to RBP. All right, so let's comment it out. And then let's append 8 Bs. All right, so this is going to overwrite RBP. And after this, we are going to overwrite the saved return address, which is RIP. So as I mentioned earlier, we need to use 6 bytes for this instead of 8. All right, so let's use 6 Cs here. And this is going to be our saved return address. All right, so once this is done, we can just print junk. Now our return to Libc exploit code starts from here. Let's update the exploit with the details that we have gathered so far. Now, before doing that, let me quickly show you a picture of how the stack is going to look like with the details that we have gathered so far. Here it is. We are going to fill in with the junk initially until we reach RIP. And once we reach the RIP, we are going to fill that in with the address of the gadget, which contains the instruction pop RDI. So that's going to be this, the Libc base plus the offset of this gadget. After that, we are going to place the address of binsh, because when this pop RDI instruction gets executed, whatever the value that is on the top of the stack is going to be popped into RDI. And we want that top of the stack to be the address of binsh. So that becomes an argument to system function. So the next 6 bytes are going to be the address of binsh. Once again, this has to be the base address plus offset. After that, we are going to place the address of system, and once the system function executes, we are going to get a shell because the argument is actually binsh. And when we exit from the shell, the control is going to be returned to the next instruction, which is going to be the address of exit function. So when this instruction gets executed, we are going to exit gracefully. So let's try to add these details to our exploit. Let's switch to the virtual machine and let's replace these 6 Cs with the address of our gadget. Before that, let's create a variable called libc_base. I'm just going to copy the address of this Libc base, which is this, and let's place it here. So that's going to be Libc base. Now we are going to overwrite this return address with Libc base plus the address of the gadget with the instruction pop RDI. So let's use pack q and libc_base plus the offset, which is this. Let's copy this and let's paste it here. Let's end it with a semicolon. We are using the option q in the pack function because we want to convert 64-bit addresses to Little Endian format. In 32-bit exploit development, we typically use L, which is used for 32-bit addresses, but in case of 64-bit addresses, we will have to use this option Q. Right, now the next line is going to contain the address of bin sh. So let's use junk and let's append it here using pack once again with the option q, and let's use libc underscore base plus the offset of bin sh. Here it is. This is the offset of bin sh. So let's quickly copy this and let's paste it here. All right. So the next line is going to contain the address of system. So let's write that here. I'm going to use q, and address of system function is this. As I mentioned earlier, it's not the offset, so we don't have to add it to the libc base. We can just directly use this address. I'm just going to the next line, which is going to be the address of exit function. Okay, so let's use pack with the same option and let's paste the address of exit here. So I'm just copying the address of exit and let's paste it here. All right, so we are pretty much done with our exploit. We have written everything that we planned earlier. Let's quickly add the comments. This is the address of system and this is the address of exit. All right, so we have pretty much everything we wanted. We begin with the base address of the libc library here. After that, we filled in some junk until we reach the RIP register, and we are adding the libc base and the offsets using Perl. We don't want to do any manual calculations as Perl can do it for us. Aside to that, we have multiple addresses which are to be written in little endian format manually. So to avoid writing these in little endian format manually, we are using pack function with the option q. Q is used to convert 64-bit addresses to little endian format. So we are just passing these 64-bit addresses to the pack function using the option q. Now let's save the file and let's try to run this exploit. I'm just going to give it executable permissions. There it is. Now let's try .exploit1.pl, cat, and let's pipe it to our vulnerable program. I'm just hitting enter. Let's hit enter once again and let's check if we have gotten a shell by typing some command. As we can notice, there is a segmentation fault. Now let's try to understand what's causing this issue. Let's run the vulnerable binary in GDB and see where the exploit is failing. So I'm just going to clear the screen and let's produce the payload so that we can use it in GDB. I'm just calling it payload 1. Now let's load the binary using GDB. Now let's set up a breakpoint at main and let's run the binary using payload 1 and let's use disas vuln function so we can set up a breakpoint at this ret address. I'm just copying this and let's set up a breakpoint at this address. Now let's continue so that we can hit this breakpoint. Look at that, we have hit the breakpoint, so the execution is now stopped, and the next instruction that is to be executed is the ret instruction, which is the last instruction in vuln_func function. Now once after this instruction is executed, if you notice, we are going to land on our gadget with the instruction pop RDI. So once this pop RDI is executed, whatever the value that is on the top of the stack is going to be popped into RDI register, which is going to act as an argument for the system function. Let's try typing si. Look at that. Now we are about to execute this pop RDI and currently the top of the stack is this, which is actually pointing to binsh, which is expected. So everything is fine until here. So let's type si, and we have a ret instruction, type si, and after that looks like we are already inside the system function. So everything is working as expected. Let's type C so that the execution will continue. And there is a problem. There is a move APS instruction here, which is actually causing this issue. On some of the 64-bit machines, this seems to be a known issue. If the stack is not 16-byte aligned while calling system function, this might happen. To fix this, we can simply add a ret instruction before the pop RDI gadget address. By executing ret, it will pop off 8 bytes on top of the stack and return to that. So it will realign the stack to 16 bytes. This blog post nicely explains this problem along with the basics of stack alignment. So I would highly recommend you to go through this blog to better understand this stack alignment issue that we have just faced. Alright, so with that, I'm just going to fix this part by adding the address of ret instruction before the address of the pop RDI gadget. So let's quickly go through how the stack is going to look like now. Currently, this is how our stack is looking like. Now we are going to add the address of ret instruction here instead of the address of this gadget. So every other address will slide down accordingly. So this is how it is going to look like. We are going to find out the address of ret instruction and we are going to place that here, and all the previously placed addresses will slide down accordingly. Right? So let's go ahead and find out the address of ret instruction using ropper. I'm opening up a new terminal. So let's use ropper, and instead of getting a shell and loading the binary, we can simply use -- file and specify the library here, which is libc, and we can use -- search and we can specify ret. So this is another way we can search for gadgets. So we have gotten the output, and if you look at this address, there is a ret instruction, and this seems like a good candidate for us. So I'm just copying this offset and I'm gonna paste it here. So this is the copied address. Just to have the full list of addresses at one place, I have just pasted it here, but we can just directly paste it in the exploit itself. Right, so let's go back to the exploit. Let's exit from this GDB shell and let's use vim exploit1.pl once again, and let's add this ret address here, junk pack, and let's use libc_base because this is an offset that we have gotten. So we will have to add it to the base address of libc. Looks like there was a typo earlier. It's a pop RDI, ret, and the current one that we have just gotten is basically ret. Alright, so this should fix the problem that we have faced earlier. So let's save the file and let's type this command, and if it works, we should get a shell. Let's hit enter once again and let's type id, and there you go. The exploit worked. Now let's try to practically understand why this address of exit is needed here. Now let's go back to the exploit once again and let's type exit. Let's type exit once again, and look at that, it has gracefully exited. Now what I want to do is I want to edit the exploit, and I will remove this address of exit. Instead, I will just add some junk. I am probably going to add 6 A's, which are 641s. That should do it. So let's save the file and let's go back to the previous terminal and let's execute the exploit once again. Once again, we have gotten a shell. Now let's exit. And look at that. There is a segmentation fault when we are exiting. The reason is after completing the system call, when the control returns to the next instruction, we have specified 6 A's as the next instruction to be executed. And these 6 A's are just junk, and thus it's causing a segmentation fault. And that's the reason why we wanted to place the address of exit immediately after the address of the system function. So that brings us to an end of return to Libc attack. Let's quickly take a recap of what we have done. We have basically enabled NX bit on our vulnerable binary, and then we have built an exploit by not placing any shellcode on the stack, but we have just made use of few addresses in Libc library. And then we redirected execution to the Libc functions, and in turn we got a shell. This is a classic example of how return to Libc exploits work.